Section 6.3, Periodic Trends. Here's the objectives. Interpret the trend shown by the atomic radii within the periodic table. Explain variations in ionization energies within the periodic table. Interpret the trend shown by ionic sizes within the periodic table. And interpret the trend shown by electronegativities within the periodic table. In other words, you need to understand the trends that take place in the periodic table that we're going to go over with. So first one we're going to talk about is atomic size. Now, you don't just go out and measure an atom with a ruler. You can't do that. And we talked about how the electrons, we don't know exactly where they are, so how do you determine the size of an atom? Well, the way that they do that is that they take two atoms and bond them together, and then they measure the distance between the two nuclei, and they take half of that. And that's how they determine the size of an atom. That's their method for doing that. Usually this is measured in picometers. That's trillionth of a meter. Okay, so we're talking very small things. And in general, the atomic size increases as we go from top to bottom within a group. So if we're talking on the periodic table, so we go from top to bottom, it increases, and it decreases from left to right. So let's take a look at the periodic table here a second. So what we're saying is, as we go down this chart, as we go down, right there, we are getting bigger. Well, doesn't that make sense? I mean, think about it. We've got hydrogen. It's got one electron. Yeah, so it's not very big compared to francium, which has 87 electrons. So that would make sense. As I go down the chart, it gets bigger. Okay? But this is kind of a little bit interesting. As I go from left to right, it gets smaller. So it actually, I'm going to always try to draw to the bigger side. So as I'm going this way, I am getting bigger. So let's take a look at this. Neon, which has 10 electrons, is actually smaller than lithium with 3 electrons. Now that might seem a little bit strange, and you're probably wondering why that would be. And let's talk about exactly what goes on here. And this is important for you to understand. I'm sure this will be questions on the test. But as we go down a level, as we go from here to here, this is my 1s1 level. Here's my 2s1 level, 3s1, 4s1 for potassium, and so on. Notice that I'm always adding another level. So think about my electron. Here's my nucleus of my electron. Got my first level. Then I got my second level. And my third level, and so on. I keep adding levels. And what happens is these inside levels, as I have these levels right here, they kind of shield the outer levels from that pull of the nucleus. Because, think about it. As I'm adding more and more electrons, I'm also adding more and more protons. So you would think, hey, if I got more positives and more negatives, it'd be stronger. But this shielding takes place. So this one is shielding the second level, and this one here is shielding the third level. And so because of that, these electrons on the outside tend to get farther and farther away because of this shielding. So shielding is kind of our key when we go down. However, as we go across, we are always in the same level. And so then what we're doing is we're adding more positives and more negatives. And so therefore, as I go to the right, I'm adding more positives and negatives. These charges get bigger and bigger. And so they pull them in more. So the smallest one, small, is up here, helium. The biggest one is down here, francium. So I always just think of it as, like Fat Francie or something like that kind of sticks in your head that reminds her it's big as France. It's big elements, as big as France. But that's our biggest one. So our elements increase as we go across, and they increase in size as you go down. Okay? So all of those things. All right, so let's go back to our slide. So we talked about that. And now let's talk about group trends. And so we talked about this already. So this here says the increase in positive charge draws the electrons closer to the nucleus, and the increase in the number of occupied orbitals shields the electrons. So as I go down, I've got shielding. I don't have shielding as I'm just going across. Okay, that's what they're talking about. Now here's kind of that. Now notice that the pattern isn't perfect either. I mean, these are general trends, and so you'll notice that sometimes they're a little bit out of order, but not by much. But notice how, as you go across, let's just say we look at lithium. You're going lithium, and then it's getting smaller and smaller and smaller until you get to neon. And then it jumps up to sodium, and then it gets smaller as you go to argon. Then it jumps up to potassium, so on. So that's the atomic radius or atomic size. So either one of those, they would be meaning the same thing. So as we go across, we're adding them to that principal energy level. Therefore, we don't have that shielding, and we just have more positives and more negatives. We have a stronger magnet pulling them in. So going across the chart, it seems a little backwards, you know, at least it's the opposite the other way, you know, of what it is if you go down the chart. All right, so let's talk about an ion. And when we're talking about an ion, we're simply talking about an atom that has either gained or lost an electron. So it's an atom, or it can be a group of atoms that has a positive or a negative charge. Either gained electron, became negative, it lost electron, became positive. And as an atom, they're always neutral, same number of protons, same number of electrons. But we can lose those or gain those electrons, and then they form ions. And usually what's happening is those electrons are being transferred from one atom to another. So let's take a look at sodium, which sodium has this tendency to lose one electron. So you can see here it's got 11 electrons and 11 protons to start with, and it likes to lose an electron. And then, you know, as you go across, notice that it gets much smaller. The nucleus as it lost, or the atom now, the size of it as it lost an electron, is much, much smaller because it actually lost an entire level. Because think about sodium. Sodium ends in 3s1. So if it lost that one s1 electron, then it goes down to level 2. On the other hand, if you look at chlorine, chlorine starts out with 17 electrons and 17 protons, and it's going to gain that electron. And therefore, it's going to get bigger because now there's more electrons, not as many protons, harder for the protons to pull it in. They're going to be able to get away a little bit easier from that. So if we have an ion that is a positively charged ion, in other words, it lost an electron, we call that a cation. And we'd simply write those with like a 1 plus or a 2 plus charge. So you'd say like Na plus or Ca2 plus. And notice that we don't write the 1 plus, you know, we don't write a 1 when we're writing Na plus, just write Na plus. And then Ca is 2 plus, and so on. Just like you don't write 1x usually, you know, in algebra. With a negative charge, we call that an anion, and we would write those with the minus 1 minus or 2 minus. So you have Cl minus or O2 minus. And if we want to talk about trends in ionization energy, in other words, we were just talking about ions. Ionization energy is how much energy it takes for that electron to be removed. In other words, if I want to come in and I want to steal that electron from that atom, how much energy is that going to take? That's the ionization energy. So we're going to talk about, there's different ones because we could take the first electron, we could take the second electron, and so on. But we're going to talk about the first ionization energy. In other words, one that's going to produce a cation with a 1 plus charge. And those first ionization energies tend to decrease as we go from top to bottom within a group, and they increase from left to right. Okay, so let's go back to the periodic table here. And we'll go over here. Okay. So what we're saying is, as we go here, let's think about this, okay? Francium, we said that was our big one. Okay, and it's got one electron way out or a long ways away from that nucleus. So it's really pretty easy to steal that electron. It doesn't watch it very closely. So on these, this ionization energy is really small, and it gets larger as I go up. Lithium, it's only got 3 electrons to keep track of. It's a lot easier for it to keep track of those 3 than it is for francium to keep track of those 87. So the ionization for lithium is much higher than it is for francium. And as we go across, remember, we added in the same level. So now we have stronger, if we're talking about neon, we have 10 positives and 10 negatives. And that's stronger than lithium, which only had 3 positives and 3 negatives. So much harder to take them away. So the highest ionization energy is over here. Now notice our last trend was to the left and down. The bigger it is, the easier it is to take it away. Therefore, the smaller it is, the harder it is. So this is just exactly the opposite of atomic size or atomic radius. Exactly the opposite. All right, let's go back to the slides.